Hello everybody, welcome into another lesson. So today we are going to talk about what is called the triple scalar product. And that's going to tie into what I have drawn over here, which we'll talk about after a couple of examples, but we're not going to start with this right away. But the triple scalar product consists of dealing with three vectors, as the name triple sounds. And scalar tells you that you should end up getting a scalar. So here you have your standard vectors u, v, and w, where you have each of their components in linear combination form with I, j, and k, your various coefficients on those. To find the triple scalar product, it's going to be the dot product of vector u with the cross product of v and w. So you're actually integrating a dot product with a cross product for this. And there's a better way to do this. Instead of doing the dot product, you can set this up just like you would for a cross product, only instead of row 1 being ijk, row 1 will be all your coefficients on vector u, all the components of vector u. Row 2 will be the components of vector v, and row 3 will be the components of vector w. So having said that, let's go ahead and do a couple of examples of how to find a triple scalar product. So these actually are not so bad to deal with. So I got two examples of this. They're really not bad at all. So what is vector u? So vector u is going to be 2i plus 3j plus k. So vector u has components 2, 3, and 1, or in linear combination 2i plus 3j plus k. Vector v is I minus j. So the y component of this is 0, but you have an x and a z component. And then of course we have a vector w, which has 4i plus 3j plus k. So you have vector u with 2i plus 3j plus k. Vector v is I minus j. Vector w is 4i plus 3j plus k. Let's go on ahead and find the triple scalar product. So to take the triple scalar product, we're going to take the dot product of u with that cross product of v and w. Now to take the triple scalar product, go ahead and set yourself up a 3 by 3 determinant. You're going to take the coefficients of each of your vectors. So row 1 is your coefficients of u. You'll have 2, 3, and 1. Vector v, you'll end up having, it has a y component, it doesn't have a z component, rather. So you'll have 1, -1, and 0. And then vector w has components of 4, 3, and 1. So you have a 0 for your z component for vector v. Unlike finding the normal cross product where you had to stick with the first row, when you take a triple scalar product, you can do this like you would a normal determinant. So pick any row, any column, and you can do that. I think we'll actually go down the third column because you're going to have coefficients of 1 and then your middle entry is a 0, so this is really going to shorten your workload. So all we're going to have are two 2 by 2 determinants. So if we go down the third column, when you take that coefficient of 1, strike out the third column and the first row, you get a 2 by 2 determinant of 1, -1, 4, 3. Now that 0 would be a minus, but 0 times anything is 0, so go right to that next coefficient of that next entry of 1, strike out the third column and third row. This will be plus the determinant of 2, 3, 1, negative 1. Now all we have to do are take two by 2 determinants, so this would simplify into 1 times 3 is 3 minus negative 1 times 4, that's plus 4, plus your next determinant, so 2 times negative 1 is negative 2, minus 3 times 1, that's minus 3. So this would simplify into 7 minus 5, giving you your triple scalar product of 2. So the triple scalar product for these three vectors is 2. So as the name sounds, break down the name. It's triple, meaning 3, of course. Scalar tells you your final result should be a scalar rather than a vector. And then the product, well, it's the product of all three. You have a dot product mixed with a cross product. All right, let's do one more of, in general, finding a triple scalar product. So let me just pretty much leave these alone. I'm going to keep the determinant format set up even, but obviously what we have here is about to change. All right, so vector u is I plus 4j minus 7k. Vector v is 2I plus 4k. Vector w is negative 3j plus 6k. Alright, so vector u has components of I plus 4j minus 7k. Vector v is 2I plus 4k, so notice it has no j, which means it has a 0 for your y component. And then vector w is negative 3j plus 6k. It has no I, so it has no x component. So we're going to take the triple scalar product of these three vectors. So the first row will be all your components of u. So you'll have 1, 4, and negative 7. Second row is your components of v, so you'll have 2, 0, and 4. And then vector w is your third row, so you'll have 0, negative 3, and 6. Well, again, pick any row, any column. You have two good choices here for either going down a row or column because you have 2 0 entries. I like to work with the smallest multiples, so I'm going to go down the first column. So I'll have a positive 1 for my coefficient for the 2 by 2 determinant that's coming up. So strike out the first column in the first row. You'll just end up getting the determinant of 0, 4, negative 3, and 6. That was plus. Now you're going to have minus 2 because you go plus, minus, plus. So this will be minus 2 times the resulting 2 by 2 determinant when you strike out the first column in the second row. That would be 4, negative 7, negative 3, 6. So let's go ahead and start taking determinants. So the first determinant is you'll have 0 times 6, which is in fact 0, minus 4 times negative 3, that turns into plus 12, minus 2 times 4 times 6 is 24, and then minus negative 7, so it turns into plus 7 times negative 3, that's actually minus 21. Let's simplify a bit, so you'll get 12 from the first set, minus 2 times 3, which would end up giving you 12 minus 6, or just a triple scalar product of 6 for these three vectors. So the triple scalar product in this case would be 6. Alright, now we found triple scalar products. Now why would you want to take one? Well, this transitions over to what we have here graphed, which is really kind of cool. And I'm about to give you a really fun name for a 3D figure. Try saying this 5 times fast as a challenge. Parallelepiped. Try saying that 5 times fast. A parallelepiped. Parallelepiped. Yeah, that can get challenging, but what is a parallelepiped? It's the 3D equivalent to a parallelogram. That's all that is. It looks a lot like a parallelogram because, well, it is in 3D. Now, the area of a parallelogram, right? That, of course, is the base times the height, which we can also call the area of the base, right? Or we just often call it the area of the base. So that means the volume of a parallelepiped is going to be the area of the base being a parallelogram times the height of your times the height of the parallelepiped. Looks very similar to finding a rectangular prism's volume, and in truth it's very similar because a parallelogram has the exact same area formula as a rectangle. So the volume of a parallelepiped would have the exact same formula as that of a rectangular prism. But having said that, how does that translate into triple scalar product? Well, the area of the base, the parallelogram, when we did cross products yesterday, that, of course, when we did the cross product, was simply the magnitude of the cross product, which in this case we'll call vector v and w. That's just the magnitude of the cross product of vectors v and w. Well, you can call the height vector u, so what you end up having is you're actually going to take the absolute value of the triple scalar product of these vectors. So the volume of a parallelepiped is the absolute value of the triple scalar product of 3 vectors. And the reason we take the absolute value is because we know the triple scalar product is a determinant, and you can get negative answers for your determinants sometimes. Well, volume and area can't be negative, they're always positive, so that's why we take the absolute value of it. Okay, so now having said that here, let's go ahead and take the volume of some parallelepipeds. We're going to start where they give you 3 vectors for your parallelepiped. So let's see here. Vector u has components of 0, 2, 2. Vector v has components of 0, 0, negative 2, and then vector w has components of 3, 0, 2. Alright, so we have a parallelepiped that consists of vectors u, v, and w. Well, I'm probably going to call vector w my length along here. So we'll call this length vector w, because that'll be the length of my base. Now we can call my width of this parallelepiped, I'll probably call this here vector v for along here. So then this length here is going to end up being my vector u. That'll be vector u to represent my height. So I have a parallelepiped with these three vectors. Now, in order to find the volume, I need to take the triple scalar product. But first, let's take just the triple scalar product. So let's take the triple scalar product of vectors u, v, and w. And this actually isn't going to be that bad. So first row of my 3 by 3 determinant, all the components of u, so that'll be 0, 2, 2. Vector v is all my is my second row, so 0, 0, negative 2. Vector w is my third row, so 3, 0, 2. Well, notice we have two columns that have 2 0 entries. I think it's a no-brainer. We probably want to use the first column because we're only going to have to do one 2 by 2 determinant. This would be positive 3, so we'll take 3 times the resulting 2 by 2 determinant when we strike out the first column and third row. So that'd be 2, 2, 0, negative 2. So this would be 3 times 2 times negative 2, well, that's going to be negative 4, minus 2 times 0, that's just minus 0. So this would turn into 3 times negative 4, or negative 12. But to find the volume, that's going to be the absolute value of my triple scalar product. So let's take the absolute value of negative 12. That means the volume of this parallelepiped is going to be 12 cubic units. So the volume of this parallelepiped would be 12 cubic units based on the absolute value of the triple scalar product. Let's do one more where the vector is given to us. Then after this, we're going to do 2 examples where we got to actually go ahead and find the vectors even. So let's see. We'll have different vectors this time. Vector u is 1, 2, negative 1. Vector v is negative 1, 2, 2. Vector w is going to be 2, 0, 1. Alright, so I have my 3 vectors that make up the length, width, and height of my parallelepiped. So we'll have vector u going along here. Vector v will cover the width of the base. Vector w will cover the length of the base. So of course the volume of this parallelepiped made up of these 3 vectors is going to be the absolute value of the triple scalar product. Well, we should probably just find the triple scalar product first, then we can take the absolute value. So the first row of this determinant is all the components of u, so that's going to be 1, 2, negative 1. Second row, components of v, so negative 1, 2, 2. Third row is going to be components of w, so 2, 0, and 1. Well, notice we have a 0 entry in either, if you want to call it the third row or the second column. I'm going to go down the third row this time, because if I go down the second column, it'll be negative and positive, which would get confusing. If I go down the third row, I'll have 2 positive coefficients, or 2 positive multiples on my determinants. So we'll take 2 times the determinant of when I strike out that first column and third row. That'll be 2, negative 1, 2, 2. Alright, minus 0, which is 0, plus 1, so this will be plus the determinant of when I strike out the third row, third column, would be 1, 2, negative 1, 2. So let's take some determinants. So you'll end up having 2 times, well, 2 times 2 is 4, minus -1 times 2, that turns into plus 2, plus my next determinant, so 1 times 2 is in fact 2, minus 2 times -1 is plus 2. So this would simplify into 2 times 6 plus 4, which is 12 plus 4, which equals 16. That's the triple scalar product. The volume is the absolute value of that triple scalar product. Absolute value of 16 is in fact 16. So the volume of this parallelepiped is going to be 16 cubic units. Alright, so those were fairly easy. We had the vectors given to us. Now they're going to throw a couple at us where the vectors are not given to us. Alright, so let's just erase all this because we're going to have 8 vertices. Believe it or not, we're about to have 8 vertices. So vertice A will be at the origin at the order 00000. Vertice B will be at 400. Vertex C will be at 4, -2, 3. Vertex D will be at 0, -2, 3. Vertex E will be at 4, 5, 3. Vertex F will be at 0, 5, 3. Vertex G will be located at 0, 3, 6. And then we got a vertex H, which will be located at 4, 3, 6. So we have 8 vertices for this parallelepiped. Well, we're definitely going to have to find the vectors. So first thing I'm going to recommend is let's start plotting points. Why don't we call this, we'll call this here 0, 0, which would be A. I'll call this right here B, which would be 4, 0, 0. And then C could be 4, -2, 3. So we'll call this C. And then we'll call this back here vertex D, which would be 0, -2, 3. And then up here, this could be E for 4, 5, 3. We'll go up here for E. Actually, this would be E back here. This one will be F if it's 0, 5, 3. So that means G would have to be 0, 3, 6, and then H is going to be back here at 4, 3, 6. All right. So we have the parallelepiped with all 8 of these points plotted. So what are we going to do? Well, here's the thing. We only really need, all we really need for this are 3 vectors. We don't have to sit here and try to find so many vectors, because the volume, we're going to find the volume of this parallelepiped. All you need are 3 vectors to take the absolute value of the triple scalar product, and you have your volume. So these problems look overwhelming, but don't let them overwhelm you, because you're actually probably not going to use all 8 points. So let's look here, okay? You have, of course, the length of your base, BC. We can definitely take a vector BC, can't we? So let's take the length of vector BC, or find vector BC. So let's see. If I take the 4 minus 4 is 0, and then if I take negative 2 minus 0, that's negative 2. Then if I take 3 minus 0, that's 3. So vector BC, we'll call this in fact vector BC. And then let's see. The width of your base you could call CD. So we should probably want to find a vector CD. So vector CD, take 0 minus 4, you'll end up getting negative 4. And then take negative 2 minus negative 2, that turns into negative 2 plus 2, which is 0. And then take 3 minus 3, which is 0. So right here we'll call that, let's call that vector CD right here. And then we can take the height, which we'll call vector CG. Why don't we do vector CG? So CG, let me move this down a little bit here. So down here would be vector CD to denote my width of the base. Now my height I can call vector CG. So if I take 0 minus 4, I'll end up getting negative 4. And then if I take 3 minus negative 2, that turns into 3 plus 2, which is 5. And then if I take 6 minus 3, that turns into 3. So here's my vector CG, which would represent my height. Now I have a length, width, base, and height. So in actuality, I could have gone over here and found different vectors and gotten the same result. But basically think of these 8 points as different options you can pick to find your 3 vectors. You're not actually going to use all 8 points. Once you've found a vector to represent your length, width, and height, it's time to take the triple scalar product and then take the absolute value of it. So if CG represents our height, we're going to take vector CG with the dot product of vectors BC crossed with CD. That would give you your triple scalar product for these vectors. So now let's set up the determinant. Take your components of BC for the first row. So you'll have 0, negative 2, 3. Second row, you'll have negative 4, 0, 0. Third row, you'll have negative 4, 5, 3. Well, would you look at that? If we stick with the second row, we have 2 0 entries, which would mean I only have to do 1 2 by 2 determinant. Well, the first term in the second row is actually negative of whatever number you have there. So negative 4 turns into positive 4 times the resulting 2 by 2 determinant I get when I strike out the first column and second row of negative 2, 3, 5, 3. So let's do the determinant work. You'll end up having 4 times, all right, negative 2 times 3 is negative 6, minus 3 times 5, well, that's minus 15. We simplify this, you'll end up getting 4 times negative 21, which would end up giving you negative 84. And then to find the volume, just take the absolute value of that negative 84. You'll end up getting the volume of this parallelepiped being 84 cubic units. So the volume of this particular parallelepiped is 84 cubic units. Alright, so I got one more example, and I think for simplicity's sake, we're going to try to keep the same vectors to represent length, width, and height. It's just your vertices and your vectors themselves will change based on the differences in coordinates. But let's do one more example. So let's see here. Let me keep that format up just to help us. I'll even keep the determinant format up. I'm just going to change the numbers because we're going to get different numbers. All right. The coordinates are about to change. Dang it. If I could go a day without dropping something, man, that'd be a miracle. So for the next problem, A still is at the origin at 0, 0, 0. B is at 1, 1, 0. Let's see. C is at 1, 0, 2. D is at 0, 1, 1. E is at 2, 1, 2. F is at 1, 1, 3. We actually may not be able to use the same vectors, but we'll still get there. G is at 1, 2, 1. And then H is at 2, 2, 3. So, you know what? I'm going to have to replot some points. I thought better of it, and let's make this make sense. I know it's not exactly drawn to scale as far as size and as far as where the actual coordinates are, but I'm going to make this make sense. That's the thing. So, A being 0, 0, I'm still putting back here. That's going to stay A. But let's see. I'm going to actually call this over here B. This will end up being B right here. So C is going to be at 1, 0, 2. Alright. Now actually we should call that D. If we're back 0 in the X, I'm going to call that D. So these coordinates are going to be a little bit different. And so are our vectors. But all we still need, bottom line, are 3 vectors. I'm just trying to make this make sense. Now let's see. I'm going to say vector E is going to be, or not vector E, point E would be right here. H would be right here. So we're 4 of them through. Okay. So I need to deal with C. I need to deal with B, C, F, and G. B, C, F, and G. So if I pick, let's see. B, C, F, and G. Where do I want to put them? I'll put B right here. I'll end up putting C right here. I'll put F here. Good, and then we'll put G right here. Okay, good. I got all the points plotted. I just wanted to make this make sense. That's all. Now, all I need are 3 vectors. That's really all I need. So, I need a length, width, and height. Well, we'll make AE the width. So if we take a vector AE, that's going to be our width. So if I take 2 minus 0, I get 2. 1 minus 0, I get 1. 2 minus 0, I get 2. So AE is 2, 1, 2. So there is your vector AE right there. Now we should probably do the length of the base, so we'll pick EH. So EH, let's see. So if I take 2 minus 2, I get 0. If I take 2 minus 1, I get 1. And if I take 3 minus 2, I end up getting 1. So there's EH right here. And then last but not least, of course, I'm going to need a height. That'll be vector EB. We'll call EB the height. So that'll end up being, let's see, if I take 1 minus 2, I'll end up getting negative 1. 1 minus 1, I get 0. And then 0 minus 2, I get negative 2. So there's my 3 vectors to represent the length and the height. So right there is going to be my vector EB. Well, of course, the volume's the absolute value of the triple scalar product, but first we need to find the triple scalar product. If EB is my height, so we'll put that outside here. We're going to take the dot product with of EB with the cross product of AE and EH. It's just being able to identify which one's your length, width, and height, so you set this up correctly. But in theory, it really doesn't matter because you're going to have a 3 by 3 determinant. It just might change which rows it goes in, but as you know, you can move rows and determinants without changing the final result. So, let's see here. EB then, that'll be my first row. The coefficients, the components of EB, so that'll be negative 1, 0, negative 2. Then AE's my second row. That'll end up being 2, 1, 2. And then EH would be my third row. I'll have 0, 1, 1. Well, I think row 3 is a great option because I have coefficients of 1 and I'll only have two 2x2 determinants. So let's go ahead and set this up here. So this would be plus, so that's actually a minus 1. So that'll be minus the resulting determinant when I strike out the third row in the second column of -1, -2, 2, 2. Then plus a 1, so plus the determinant of when I strike out that third row and third column, that would be -1, 0, 2, 1. Alright, let's do our determinant. So this would end up being negative of -1 times 2 is in fact -2 minus -2 times 2. That would end up being plus 4. Plus this other determinant, so -1 times 1 is -1, minus 0 times 2 is 0. So this would end up turning into -2 minus 1, which would end up giving you -3. Well, the volume would be the absolute value of that -3. So the volume of this parallelepiped is actually just going to be 3 cubic units. So the volume of this particular parallelepiped is 3 cubic units. Alright, so that's it for this lesson. We only have 3 more lessons left in the course. So we should be finishing in a few days Precalculus and then going on to Calculus by the middle of the coming week. But the next lesson itself is going to be about lines in space and finding equations of lines in space. It's a little bit different than doing it in the XY plane because you have the whole Z element. So I hope everybody has a great day. Take care.